In this video, we're going to begin our discussion of antiderivatives. So, looking at the word antiderivative, we've been dealing with derivative for the duration of calculus, right? In the parts that we weren't talking about limits, but this prefix anti means opposite. So, instead of taking the derivative, we're almost going to take this derivative process that we've been doing for the past couple of chapters and reverse it. So, essentially what we're given here is we're given a solved for derivative in a sense, and we're trying to find the function that spawned this derivative almost, if that kind of makes sense. So we're taking the derivative process but thinking about it backwards. And so what we're trying to do is we're trying to find this general antiderivative, or this f of x, such that this capital F prime equals f that we're given here. If we can find a capital F function such that if we derive it, it returns this original function that we have here, then we have that f is an antiderivative of little f. So little f is essentially the derivative of capital F. We can kind of think about it that way. So what we're going to try to do is think about the derivative rules and processes that we've been using up to this point and see if we can almost flip them around to come up with the function that spawned this thing, this derivative that we have in front of us. And what we're looking at for this first case is we have a polynomial as our kind of our function that we're given here, right? And so when we're dealing with polynomials or terms that have powers on them, how do we usually obtain a derivative with a bunch of powers, but using the power rule, right? So what we're seeing here is that this f of x is almost seen as the derivative of capital F, and to find the derivative of capital F, we use the power rule in a sense on the original f to obtain this lowercase f, right? So we're almost going to think about the power rule here, but in reverse. So normally what we do with the power rule is, if we were to take the derivative of something like x to the n, we would bring this power down and then subtract 1 from the power, right? This would be the power rule for differentiation. What we're almost going to try to do now is think about this in the opposite way. And what that entails is we're going to increase this power by 1. Okay, so this will kind of go back to being n. But then in order to compensate for this coefficient, what we're going to need to do is divide by the original new power that we have. So if we're trying to find the antiderivative of something like this, we're going to need to increase this power by 1 and then divide the new or divide this term by the new power that we have in a way. So that's kind of what we're going to do here. So in each term, because we know that we can take the sum of the derivatives and that equals the derivative of the sum and the difference, all that kind of good stuff, we're going to take the derivative of each piece, or the antiderivative rather, of each piece. So we're going to look at this piece, and then this piece individually. So using the thinking that we talked about, if we're trying to obtain a capital F function, such that if we derive it, we get back to this, what we're almost going to do is we're going to try to increase the power by 1 on this x term, so we get x to the third. The constant multiple stays in there, but we're going to divide by that increased power that we have here to compensate for the fact that we have raised the power and we're trying to do the opposite of differentiation. We're trying to go the opposite direction with differentiation. Okay, so we're going to have something that looks like this. If we raise this power by 1, we're going to get 3. So we're going to need to divide this whole term by 3 as well, by that new power. So we're going to kind of keep that train of thought going as we move along, taking all these other things. So we're going to increase this power by 1 and then divide the term by that new power as well as a coefficient. And then lastly, we're going to do it for this last one. So we're going to increase the power by 1 and then divide this term by that coefficient. So now we have this, and it looks kind of messy. So let's see if we can simplify this down a little bit. So we're still going to have that capital F of x equals, and we have a fraction here divided by something that we can write as a fraction, right? And the same thing kind of going on here. So when we do fractions divided by fractions, we multiply by the reciprocal of the denominator, right? So what this is going to turn out to be is something like multiplying by a third in the top and bottom of the fraction. These cancel out on the bottom, so we're just left with the top. And so now we see that this 3 and this negative 3 up here, I kind of covered up that negative that was there, they divide away to give us 1. So what we're going to be left with is negative 1 over 10 x to the third for our first term, right? But then this one, we don't really have fraction division, right? We just have x 11 over 11, so we can write that as this. So we have that going on for us. And then the last term, we're going to do that same kind of multiply by the reciprocal trick to simplify this complex fraction here. So these divide away, and then again, 8 divides away with 8, so all we have left is 1/3 x to the 8. Now remember how with antiderivatives, we always have to compensate for the fact that there was maybe a arbitrary number of, say, 3 square root of 5, something that evaluates to a constant, that when we took the derivative of that original function, it evaluated to 0. So when we're taking the antiderivative, we always have to have that plus c at the end of it, right? That constant of integration, that arbitrary constant value, this plus c, tells us that if we were to derive this to check and see if it matches back to little f of x, which we will, we'll take the derivative of this here in a second. When we take the derivative of this, this plus c will evaluate to 0, so it won't affect any of the x terms that we have, but we need to account for it to give us the general antiderivative, or the family of antiderivatives that this derivative could spawn from. Okay, so don't forget that plus c at the end of it. So now that we have a function here that looks kind of like something that we could derive to get this, let's check and see what it gives us. So let's take f prime of x just to check it. So here we're going to check our answer. So let's take the derivative of this. Let's use the power rule. So we're going to bring this power down. We get negative 3 over 10 x squared. First term checks out. Okay, let's keep going. So then we bring this power down, so we get 11 over 11, or just 1. So all we're left with there is x to the 10. Second term's good. Let's check that last one. Bring this power down, multiply with the coefficient, and we get this. And that constant, like we said, evaluates to 0 when we derive. So we see that, in fact, capital F prime does evaluate to f of x. So that tells us that the capital F that we have right here is our antiderivative for this function. So when we're trying to find general antiderivatives, we're going to look at the function that we're given and think, okay, this is the derivative of some function. Let me find that some function. So what it's going to entail is flipping around a lot of the processes that we've used to solve derivatives or solve for them, just flipping them around to see what type of function spawned the derivative that we have in front of us. So that's what we're going to look at. That's what we looked at in this video, and that's what we'll look at in the other video for this section.